Okay, let's think about defining a few terms in this video, and we'll be talking about noise floor and signal to noise ratio. Okay, imagine you have a system, just any system, a black box for now. You don't have to worry about what's inside the system. It's got some input, and perhaps the input itself has some noise. Okay, and you give that input to your system, and the output is an signal, output signal along with noise, right? What happens if you do not give any input to the signal? You have powered the system on, but you don't give any input. Okay, even then, what you usually get in systems is you don't get any output because there is no input, but you get some noise, right? And that is called the noise floor of the system. So the noise floor is the noise that you get in a system output when there is no input connected to the system. Okay. Now, why is that important? Now think about it. So if you have an input-output relationship, so this system which takes an input and gives an output, right? Now, what is the minimum output that would correspond to the input that you have given? It's going to be limited by the noise floor, right? Because even without any input, the output is going to be equal to the noise floor. Okay, so there is some noise there. You want to give a big enough input so that your output is above the noise floor. If it isn't, you cannot distinguish a no input condition from an input condition. Okay, and you can see that how this idea of noise floor also relates to resolution that we talked about in sensors and signal conditioning. Okay, so the output then, the range of the output in your system is going to be from the noise floor till the saturation voltage. Okay, it's not from zero to the saturation voltage, it's from noise floor to the saturation voltage. And hopefully your noise floor is very small and it's almost equal to zero in the circuit that you are building. Okay, so let's talk about then signal to noise ratio. So as we said, in this particular system, you can have input and probably there is some noise associated with the input, and the output is also going to be associated with the noise. So what we want to do in both these cases, in the case of input and output, you see you have a signal and you have a noise, right? So what you want to do is you want to say, okay, how much power in the signal that we are measuring, because it's not as if, because when you're measuring the output, for example, you're measuring the signal and the noise in one particular as one signal. You can't really separate those two out. But when you're measuring that signal, I want to talk about, okay, how can I, how much of the power in this signal is because of the signal and how much is it because of the noise, right? And that is defined by the term called SNR, or signal to noise ratio. As you would imagine, what you want ideally is the noise power to be as low as possible and the signal power to be as high as possible. Okay, so that's what we want. But of course, you know that we'll have to compromise because of various factors. Okay, so SNR is defined as signal power over noise power, and usually we measure SNR in dB, in decibels, and SNR is given as 10 log to the bar base 10, sorry, log base 10 signal power over noise power. And when you are defining this in terms of RMS voltages, you can say 20 log uh, the the RMS value of the signal divided by the RMS value of the noise. Okay, so that's signal to noise ratio.